Alright, this video is on using KSP to predict the formation of a precipitate. We're on a solubility equilibrium packet, and this is the third and final video in covering these lecture notes. So far we've talked about what KSP is, how to calculate KSP, how to calculate molar solubility. Then we talked about the common ion effect and how the addition of a common ion to a solution of a slightly soluble salt will always decrease its solubility. And then the third idea is this video, which is I'm using the value of KSP to predict the formation of a precipitate. So your background information, or I guess maybe not background information, but the idea here is, okay, so say we had two aqueous solutions, sodium sulfate and barium chloride. And we know that if we mix those together, we form barium sulfate, which is a slightly soluble salt. So the question here is, how do we know if the barium sulfate will precipitate or not in this case? Okay, so it's possible that the barium sulfate would precipitate, but it's also possible that the barium sulfate would not precipitate. We know that it's slightly soluble. So the question is, how do we determine that? Okay, and so the answer is looking at the value of KSP for the slightly soluble salt versus the Q value. Okay, the same Q as reaction quotient calculated when we're unsure of the equilibrium status of a mixture. It's the same idea here. Okay, so and we'll do a problem with that in just a minute. So, of course, if we have a situation, which this reaction would give us a situation where, mixing the sodium sulfate and the barium chloride would give me some barium ions from the barium chloride and would give me some sulfate ions from the sodium sulfate. But the question is, would it precipitate or not? Okay, and so, of course, the solubility equilibrium that's established would be the barium sulfate equilibrium. So there it is. And I know my KSP expression looks like this. And so, of course, we have three situations. What I want to do is calculate the value of Q. And the Q value would come from what's the concentration of the barium ion from the situation of the reaction, and what's the concentration of the sulfate ion from the reaction. That would give you your Q value, and then you would look and compare your Q to your KSP. So, of course, we have three situations, just like we did when we compared Q to KC or KP. So of course we have where Q can equal KSP. Okay, and if that's the situation here, just like before, the reaction is at equilibrium. And what this means is it's a completely saturated solution. Okay, it's the highest concentration of the ions without forming a precipitate. Okay, so if your Q value were to equal your KSP value, your reaction's at equilibrium, there would be no precipitate, but that would be the highest possible concentration of the ions. And then, of course, I have two scenarios that are the two that you're much more likely to come in contact with, which are what if Q is less than KSP, and then what if Q is greater than KSP? Okay, so just like before, if Q is less than KSP, right, that means your value of Q is too small. It needs to increase. And so for Q to increase, P over R, your products would need to increase, your reactants would need to decrease, and so your reaction would shift to the right. Okay, well, if your reaction is shifting to the right, you're creating the ions, okay, which would result in no precipitate formation. So reaction shifts right, and we would have no formation of the precipitate because we would be creating the ion form, okay? But then the reverse is true. If Q is greater than KSP and we need to decrease the value of Q, the reaction will shift left. And if we have a reaction, that shifts left and creates the solid form, then we have a precipitate that forms. Okay, so again, just like we talked about in Q versus KC or KP, there's no reason to memorize these situations, it's just a common sense approach to thinking about it. What's going to happen if, the Q is too big or Q is too small? Which way is that reaction going to shift? Okay, so again, there's no need to to memorize them. Okay, so let's do a problem so you can see the type of, problem that would be asked. All right, so if you flip over, we have two problems we're going to do. And the first one says, will a precipitate form when 0.5 liters of 0.002 molar barium nitrate is mixed with 0.5 liters of 0.008 molar sodium sulfate? So we could write the reaction, the regular reaction, and I guess I will. And so this is the example we were talking about. Right. So of course what we're looking for is what's the slightly soluble salt that we're looking at in the situation, and will it precipitate or not? And of course in this case it's the barium sulfate, and we're questioning, is it going to be a precipitate? Okay, we know this thing is very soluble, so that's not the equilibrium status that we're questioning. We're questioning the slightly soluble salt, which is the barium sulfate. Okay, so knowing that, we are very interested in the equilibrium that occurs between the barium solid and its ions. And I looked up, because I don't think it gave it to us. No, I looked up the KSP for barium sulfate in the textbook, and it's 1.1 times 10 to the negative 10. Okay, so that's like a given in this case. Okay, so what I need to do is I need to calculate a Q. Okay, so I'll write myself a note. Need to calculate Q. All right, and Q is going to be equal to the concentration of the barium times the concentration of the sulfate, right? Just like it was the KSP expression. But I need to calculate these numbers from what was given to me in the problem. And then I will compare that value of Q with KSP and make a determination as to whether or not I will form a precipitate. So again, these are concentrations, right? So I need moles and liters, which I was given, so everything should be fine. So let's look at the barium nitrate, which of course is going to be my source of barium, right? That's what's important in this case, not so much the nitrate, but the barium nitrate is going to give me my moles of barium. So let's see, what did they tell me? That I had hold on, I got confused. I'm looking at the wrong thing. Okay, there it is. So I had 0.5 liters of the barium nitrate, and it was 0.002 molar. Okay, so I know, of course, taking my molarity times my liters, that if I multiply those together, that I will get the moles of that compound. Now remember, it's not really the moles of the compound that I'm interested in. I'm really interested in the moles of the barium, but that's a 1-to-1 ratio, right? 1 mole of the whole thing gives me 1 mole of barium. So I'm going to go ahead and label this as those are my moles of barium plus 2. Now, I don't want my moles though, I want my concentration. And so I have to take my moles and divide by my volume, but this is by the total volume, right? Once the two solutions have been mixed. And so I had a 0.5 liter and a 0.5 liter, which conveniently gives me 1 liter. That's nice. And so my molarity of the barium ion is just 0.001. And that's the value that I'm going to plug into my Q expression. And I have to do the same thing for the sodium sulfate, and that's all there is to this. So it's a nice review of the molarity. Okay, so moles of the sodium sulfate, which really I'm interested in just the sulfate. So it was also 0.5 liters times 0.008 molar. That gives me 0.004 moles of the whole thing, right? The sodium sulfate, but I'm really interested just in the sulfate, so it's a 1-to-1. And again, I'm going to divide that by the total volume, which is 1 liter. It's the same number. Oop, that's capital M, moles. Molarity. Okay, and then I have my two concentrations, and so I can come up here and plug them into Q. I'll drop down here and do it just so that it's not super messy. So I'm going to take the concentration of the barium, which was 0.001, we determined it to be, times the concentration of the sulfate, 0.004. This is my Q. Comes out to be 4 times 10 to the negative 6. And then we compare Q to KSP. Okay, and we reference what we just talked about. So in this case, Q is much larger than KSP. Okay, which means my Q value is too big, right? Remember, Q is products over reactants. So I need to lessen that. So I need to decrease my product and increase my reactants, right? So since Q is bigger than KSP, the only way I can increase my reactants and decrease my products is if I shift this reaction this way. So reaction shifts to the left, and because it shifts to the left toward the solid salt, we get a precipitate. Okay, so in this case, yes, a precipitate occurs. And that's how you do a problem where you consult a KSP value and you calculate a Q and you decide whether or not an equilibrium reaction, if a reaction will result in the formation of a precipitate. Okay, there is a second one. I'll do the second one because I think it's, worthwhile to have another example. Okay, so in this case we have, element we don't see very often. And potassium iodate, and we're looking at who the slightly soluble salt is going to be. It's definitely not potassium nitrate, right? That's soluble. It's going to be this thing. And that's this is +3, so okay. So this is the one we're questioning. Will we form a precipitate in this reaction? So the equilibrium that I'm interested in studying here. They told me that KSP for this compound is 1.9 times 10 to the negative 10. That was given to me in the problem. So again, I'm going to calculate Q value and compare Q to KSP and figure out if this thing precipitates. So I'm looking for moles of my first compound here by taking, just like we did before, the molarity times the liters. So that molarity was 0.004. My liters were 750 mils, so 0.75 liters gives me 0.003 moles of the whole thing, but also the ion, because it's a 1-to-1 relationship. This time they weren't so nice to me. I had a total volume of 750 and then 300, so it's 1,050 milliliters. So my total volume is 1.05 liters. So I need to take that into account here. Do my math, and I get concentration of this. And then same thing to find the iodate concentration. So my molarity was 0.02. My volume was 300 mils, so 0.3 gives me 0.006 moles of the whole compound, but also of the iodate because it's 1-to-1. My total volume is still the same. That has remained unchanged. And I got a molarity of 0.00571. And then I'm just going to take those concentrations and plug them into my Q expression, but being very careful because don't mess this up. That in this case, this value is cubed from the coefficient. So just make sure you cube the right one, or you'll get a incorrect answer. doing that on the calculator, making sure we don't hit any wrong buttons. I got something along the lines of 5.3 times 10 to the negative 10 for my Q, and then this is where we're going to compare Q to KSP. They're very similar this time. Okay, it's not as different in the two values, but in this case, my Q is slightly bigger, right? I can disregard the 10 to the negative 10 because it's the same. So the 5 is slightly bigger than the 1.9. So this is the second time we've seen this, that Q is greater than KSP. Reaction will shift left, and because it's shifting left to the solid, a precipitate does in fact occur. Okay, so that's how you can use the value of KSP and the value of Q to decide whether or not a reaction will result in the formation of a precipitate when you have something that's slightly soluble.